Oh, you got a common denominator. Yeah, so Kevin said, let's try to, you can't see? Kevin said, let's get a common denominator here. So multiply by Tn minus 1 over 2. I actually think this is really cool what he did. He got a common denominator, and then he sort of simplified it a little bit. And then he said, okay, eventually he realized that let's just call this thing x. So there's actually a simpler way. Everything he did is awesome and it's right. But is a little bit of a simpler way to do it. Okay. What's going on here is we have some sequence in which the terms are generated like this, right? Over 2 plus 1 over t sub n minus 1. And so what it means for this sequence to have limit root 2, what that means is that eventually, if you go out far enough, reciprocating and adding that to half of the number is going to barely change that number. Okay? So if this sequence has a limit, we haven't proved that it has a limit, but if it does have a limit, then the limit must be some number which, upon performing this recursive rule, barely changes that number. We did something kind of like this the other day. And so I'm looking for a number such that when I divide that number by 2 and add it to 1 over that number, what I get is basically the same. Okay, so solve this sort of equation-y type thing for x. What number, do you know any numbers which when you divide them in half and add them to their own reciprocal give you basically the same number back again? Subtract x over 2 from both sides. Magic x squared, cross multiply. Kevin's just a little bit easier version of what you did. He did essentially the same thing, but he sort of figured it out after he'd already done a bunch of unnecessary stuff. But yeah, this number, the limit of this sequence must be root 2, because root 2 is the only number which when divided by 2 and added to the reciprocal of itself gives you basically the same thing back. Okay, cool. And number 3 is kind of like the same thing. Who did number 3? Somebody did.
It's the same handwriting.
Oh, it's also the mysterious masked Kevin. Kevin says, all right, well, what is root 1 plus root 1 plus root 1 plus? You were supposed to just play around on your calculator and observe that it was phi. Kevin says, I accept your challenge, Mr. Rose. I will prove that it is true. He says, all right, we'll take root 1 plus root 1 plus root 1 plus and just temporarily call it x. Well, I see an x hiding in the formula for x, right? Because if x is root 1 plus root 1 plus root 1 plus, then x is just root 1 plus x. Everyone get it? So then he says, all right, now I have an equation, square both sides, algebra, it's phi. So good. Okay, how are we feeling about limits? Connor, good? Okay, good. Also, there was a, what's it called? Worksheet. How'd that go?
Yeah, it said
let's do this really fast. So we have to prove.
Hi, Mindy.
As n goes to infinity of 1 over the cube root of n minus 2 is negative 2. Okay, how can we do this? Well, first let's make a picture. So here's like the picture maybe. Here's negative 2. And let's see, what does I think that the limit is negative 2. What is the first term of this sequence?
Oh wait, yeah.
Negative 1, right? Is it negative 1?
It's
Yeah. Yeah, because if I take the cube root of 1, it's 1, 1 over 1 is 1, 1 minus 2, negative 1. Okay. And now, like, I have gross numbers, so now I'm going to skip to, like, the 8th term of the sequence. What's the 8th term of the sequence?
Wait. Can't do math, sorry.
You can do math, man. You got it.
It's like -2.
Yeah, good job. It is. The cube root of 8 is 2, so it's 1/2 minus 2. So it's like -2 plus a half. Okay, so here we are, over here. And then like I'll go out to like 27 next, I guess. If I plug in 27, what do I get? Down it again.
Wait, what?
What?
-1, 2/3.
One-third of
Yeah, that's right. Yeah, -2 now plus like a third, right? Okay, so do you guys kind of feel what's going on here? I do think that the terms are getting closer and closer to -2, but like slowly, very slowly. Do you sort of feel that you have to go out quite far relative to the other sequences we did last class before things get really, really close to -2? In fact, it might be worth it to use some just like, common sense or whatever, and try to like think of try to maybe figure out the pattern in advance. For example, if someone gives me an epsilon of 1/10, how far out do I have to go? Using your like wits. No, that's not what I want to say. Yes, it is. No, yes. Yeah, that's right. I'm gonna have to go out all the way to 1,000 just in order to meet their demand of being within 1/10. Because the cube root of 1,000 is 1/10. Is everyone can I get some vigorous head nods? Okay. Whoa! What if someone gives me an epsilon of 1/100th? How far out do I have to go now?
Million.
A million. Yeah, that is correct. I'm going to have to go all the way out to 1,000,000 now, because the cube root of 1,000,000 is 100. Are you guys kind of feeling this? Okay, good. So, if someone gives me a tiny number, in general, how far out do I have to go? If someone challenges me with an epsilon, how far out do I have to go?
1 over epsilon.
1 over epsilon cubed. Okay, cool. So basically the point is, I've already put some of my own independent thought into this prior to even starting the proof, so I now just like get it, and now it's just a matter of like doing it. Okay, how do we do it? Well, I have to prove things. And specifically what I have to prove is that for any possible epsilon, so that's -2 plus epsilon, -2 minus epsilon, for any possible epsilon, I can go out far enough such that beyond that point all the terms will lie between the parallel lines. Okay, so I'll just write this out, what it is that we need to prove, because I made you do it, so I'll do it too. We need to prove that for all epsilon greater than 0, there exists an n greater than 0 such that for all n, for all little n, if I go out past big N, then the difference between the nth term of my sequence and -2 will be less than epsilon. That is what I have to prove. Okay, and this proof comes in 2 steps. There's first the discovery phase. The discovery phase is not actually part of the proof. The function of the discovery phase is to discover the relationship between n and epsilon. Now, I kind of think we did this already, so technically we could skip the discovery phase, but you're not allowed to because I say so. So we just have to do it. So because also it's helpful. So what is in the discovery phase? In the discovery phase, you discover the relationship. And so what we should do is start with what we're trying to prove and try to work backwards. So I'm going to start with what we're trying to prove. That the difference between the nth term and -2 is less than. By the way, raise your hand if you feel like you did this whole Friday, you got it all right, and you're like, all good. Most people, raise your hand if you got stuck, like you got lost halfway through, you thought you knew what you were doing, but then you like decided you didn't. Okay. So am I going too fast, too slow, just right?
It's fine.
Okay, so I'm starting with the thing that I'm trying to prove, because that's going to help me. So, okay, so let's actually do it. What is a sub m? It's 1 over cube root n minus 2. And then that's the nth term, and then we have like a plus 2 in there. Okay, well of course this just turns into absolute value 1 over cubed root n. And now, this is like a little bit subtle, but basically n is always positive, so the cube root of n is always positive, so the absolute value of that is positive, which means that these absolute values are really just like irrelevant. And so I have this is true, and now what should I do? He wants to reciprocate first. Everything's positive, so if we reciprocate, then we flip the sign. And now finally, cube both sides, which is again inequality preserving, as long as everything's positive. Okay, so what we have really just accomplished is we started with the terms of the sequence in between the parallel lines where they belong, and what we determined is that seems to be happening whenever n is bigger than 1 over epsilon cubed. This is the whole point of discovery phase. If n is bigger than 1 over epsilon cubed, it seems to be that the thing that we wanted is satisfied. So if that's the case, then what's the answer to the question, how far out do I have to go in order to make this true? That far, right? The conclusion of discovery phase is that I should set big N equal to 1 over epsilon cubed. Why is that what I should do? Because if I go bigger than 1 over epsilon cubed, it appears that the thing that I wanted to prove is like true. Get it? Okay. So now we have to do the actual proof. In the actual proof, we're not allowed to like write things backwards and kind of screw around and guess and hope. We have to actually do the proof. So the actual proof goes like this. I need to prove that for any possible epsilon, blah, 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 blah. And so what we do is we're going to take arbitrary epsilon greater than 0. In other words, I'm going to imagine that someone in the audience is like shouting out epsilon. And what is my response to that person?
Boo.
Boo, and then set n to be
1 over epsilon cubed.
Yup. So whatever tiny number you give me, I'm going to cube it, which makes it even tinier, and then reciprocate it. And that is how far out I'm going to tell you to go. All right. Having done that, what must we show? We must show that if I go out beyond that number, then the terms of my secret. This time I'll do it without absolute values, just to show some variety. Because some people don't like the absolute values, they find them annoying. What I'm going to do, if n is greater than, I'm going to show that the nth term lies between -2 minus epsilon and -2 plus epsilon. That is what we need to prove. Okay, ready? Let's prove it. How do you prove a conditional? There's only one way to prove a conditional. You assume the antecedent and you derive the consequent. So we'll go to the word assume or suppose or something like that. Should definitely be on your paper. We're going to go out beyond that point big N. So if this is true, then by the definition of big N, that's 1 over epsilon cubed. And now I just kind of like repeat backwards the steps from discovery phase. That's why this shouldn't be like so hard, right? If N is bigger than 1 over epsilon cubed, then what I can now do is take the cube root of both sides. I can now reciprocate. And now I'm kind of like here, right? And then, okay, now things get a little interesting because what I want to say, I guess what I really want to do is I want to say that this is between negative epsilon and epsilon. Is that allowed? I think it is, right? 1 over cube root n just is going to be bigger than negative epsilon. Why? Because it's positive, and epsilon is also positive. So every negative number is going to be less than every positive number. And so if I now take these two inequalities and join them together by the definition of compound inequality, it must mean that 1 over cube root n is between negative epsilon and epsilon. Does that logic all make sense? I think it's good. So you have to write a little bit more if you want to avoid using the absolute values. Some people like the absolute values, some people find them annoying. So now, how do I finish it off? How do I finish it off? Yeah, sound.
-2 from all words.
He says take -2 subtract -2 from all sides. And now that just is the nth term. And so indeed we have shown exactly what we set out to show. That the nth term of this sequence lies between -2 minus epsilon and -2 plus epsilon. Alright, how are we doing? Carl, you good? Alright, you're gonna do the back for homework. Can I have this, the limit stuff? And can you write something on the top? Can you write like something like infinite sequences, assignment number 1 or something like that? Do your homework. Yeah, write infinite sequences number 1 and hand it in right here next to Mark. Yo.
I suck. Okay.
Why?
I don't know.
Wait, you take spin. You yell at me for being tired. No, why don't you? I'm tired right now.